In this lecture, the structure and composition of the Sun are discussed. The learning goals are to understand the concept of hydrostatic equilibrium and the names of the layers of the Sun, as well as the chemical composition of the Sun. Plasma is the fourth fundamental state of matter, the others being solid, liquid, and gas. A plasma is a gas that is made of ionized particles. A plasma can be created by heating a gas or subjecting it to a strong electromagnetic field. The ionized particles in the Sun have lost electrons due to the extreme temperatures. Being charged, the particle motion creates a current which gives rise to magnetic fields, which in turn constrain and change the motion of the particles. We've already discussed some of the properties of the Sun. Its radius is about 109 Earth radii. Its luminosity is about 4 times 10 to the 26 watts. Its temperature is 5,770 Kelvin. The Sun has a surface temperature around 5,777 Kelvin. Its peak wavelength is the yellow-green region of visible light, and above the atmosphere, the Sun looks white. The solar spectrum measured above the Earth's atmosphere shows the absorption features that indicate this G2 star is composed primarily of the elements hydrogen and helium. Spectral studies show that the mass of the Sun's atmosphere is 74.9% hydrogen and 23.8% helium. All elements heavier than helium are called metals in astronomy and account for less than 2% of the Sun's total mass. Detailed spectra show that the most abundant heavier elements are oxygen, carbon, neon, and iron. The presence of these heavier elements reveal that the Sun is a second-generation star in the universe and formed from the remnants of a supernova as the first-generation star died. The Sun produces a lot of ultraviolet light, which luckily is filtered out by the Sun's atmosphere. The yellow area of the curve shows the irradiance leaving the Sun, while the red area shows the light that reaches sea level on Earth. The solar spectrum that we experience has regions that are removed by water, carbon dioxide, ozone, and other molecules. The energy distribution at Earth's surface is 5% ultraviolet, 43% visible, and 52% near infrared. Figure 11.2 shows a cutaway of the Sun. We only see the outer layers of the Sun, a G2 star. Our knowledge of the history of the solar system shows us that the Sun has existed for billions of years. Physics tells us about the interior. The structure of the Sun is caused by a balance between forces due to pressure and gravity. At each location in the Sun, some physical quantities are equal to one another. When this happens, we say things are in equilibrium. Any gas at any temperature has a pressure. We are accustomed to thinking that the pressure of the atmosphere about the pressure of the atmosphere or the pressure in a bicycle tire. Consider a small parcel of the Sun somewhere in the interior. It is an inward force from the gravity of the Sun. There is an outward force or pressure from the nuclear reactions taking place at the core. These two forces must be in equilibrium. If they were not, the Sun would either collapse in on itself or blow itself apart. Knowing the mass and radius of the Sun, we know that the gravitational force is produced. Since the Sun is in equilibrium, this means we know the amount of force necessary to keep the Sun in equilibrium. The only reactions that can produce the necessary force are nuclear reactions. Since we also know the Sun is primarily made of hydrogen, the reactions occurring at the center must be hydrogen fusion. Mathematical models, consistent with the observation and physical principles, provide further information about the Sun's interior. This allows us to calculate what's happening in the interior with our understanding of how matter emits light as a function of temperature, how light interacts with matter, and how different gases behave with pressure or temperature. The Sun's nearly constant existence for billions of years is evidence that the Sun must be in balance. We understand this balance as hydrostatic equilibrium. The prefix hydro indicates fluids such as liquids or gases, and the suffix static indicates that there is steady balance inside the Sun. In equilibrium, inward gravitational force must be balanced by outward pressure. As seen in figure 11.2, density, pressure, and temperature decrease away from the center of the Sun. Energy production peaks at the center, the core of the Sun, where the temperature and pressure are highest. In the next lecture, we'll see that the temperature reaches and exceeds the critical 10 million Kelvin for fusion to take place. The Pearson figure on the right shows solar density and temperature according to the standard solar model. Our standard model of the sun's temperature, pressure, and density leads to a layered structure with a dense, extremely hot core where fusion takes place, surrounded by a less dense radiative zone, surrounded by a less dense convective zone, enveloped by several layers that collectively comprise the solar atmosphere. The sun's light and energy particles are constantly escaping, causing a solar wind that extends way beyond the orbits of the outer planets, carrying with it the magnetic field produced by the motion of charged particles in the rotating sun. In addition to the motion of material via convection, our direct knowledge of the sun's interior comes from neutrino measurements discussed in the next lecture, and measurements from helioseismology. There are sound waves that move through the interior of the sun, causing it to move up and down like a drumhead. Helioseismology is the study of the sun by analysis of these sound waves. Doppler shift gives us the speed of the waves. Helioseismology gives us an important test of the models of the sun. The sound causes waves to appear on the surface of the sun. The waves also pass through the sun's interior. We can measure the speed of the wave motion on the surface of the sun spectroscopically using Doppler shifts. These speeds are quite small, typically a fraction of a meter per second. The waves travel at various speeds, just as water waves do in the ocean. These speeds depend on the composition of the sun, particularly the ratio of hydrogen and helium to heavy elements, and the depth of the convective zone, i.e., what fraction of the sun's radius is in the convective zone. The models of the sun lead to predictions for the sound speeds and the size of the wave motion. Theory and observation agree to a very high precision, confirming that we have a very good picture of the sun's interior.